Conservation of energy. Well, and what we're talking about is mechanical energy. Now, mechanical energy is either potential energy, which can either be elastic, spring energy, or gravitational potential energy, either one, or kinetic energy. Now, in general, energy has to be conserved. And what that means is anytime we do something, I can't lose energy. In very rare cases, but unless we're splitting atoms and stuff like that, it doesn't happen. I can gain energy from mass. That's that E equals mc squared equation. But we're not really talking about that right now. What we're talking now about mechanical energy, which is energy of either position or state. In other words, what state is something in or what position is something in, or energy of movement. And right now what we're going to do is compare those two. Right now we're going to ignore friction. We'll bring friction in a separate category later. Basically what I'm going to say is the energy before something happens is equal to the energy after something happens. And when we're solving problems, energy is probably the first thing you want to use when you're working on stuff, because the formulas are fairly easy. So if energy will work, it's easier than some of the kinematics and dynamic stuff. Basically what you're going to say is the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. Excuse me. So I want to attack problems from that point of view. Now there's three cases that you can run into a lot. Number one, something swinging like a kid on a swing set, swinging back and forth from there to there, swinging through angles. So this would be your kid sitting there on a swing set like that. Oh, look at that artwork. It's a thing of beauty. And you're swinging like that. What happens is up here, momentarily the speed is 0 as you change directions. Since the speed is 0, the kinetic energy right there is 0. Here, though, your height is max, so therefore your potential energy is max. When I get to this point down here, it's the other way around. H is 0. Remember, we have the ability to call 0 wherever we want. So if I call that point to have an H of equal to 0, that allows me to say down at the bottom there's no potential energy and kinetic energy is max. And then it simply trades back and forth as it swings. Maximum KE, maximum PE, 0 KE up here. Down here we have maximum kinetic energy, potential, kinetic, potential, kinetic. At any point in between, you're going to have both potential and kinetic energy. Now, another case that is a good way to understand it is roller coasters. And I hope at some point in time everybody's been on a roller coaster like that. At this point in time, you're going to have max potential energy. Your kinetic energy is going to be a minimum. Now, in a real world roller coaster, it's not going to be 0 because you wouldn't go down the hill. Remember, in roller coasters, what you do is you do work here. You add energy. There's a motor that pulls you up to the top of that hill. When you get to this point, what you have is maximum potential energy, minimum kinetic energy. In a perfect world, we could say the kinetic energy is equal to 0, but if you had no kinetic energy, you would just stop right at the top of the hill, and you don't have that. Every peak beyond here has to be less than that. If I ignore friction, what would happen then is the energy at any point would stay consistent. So if I have 1,000 joules here, I'm going to have 1,000 joules here. I'm going to have 1,000 joules here. You get the point. The difference is it's going to equal to potential and kinetic energy. Down here, it's going to be all kinetic because the potential energy is 0. Up at this point, it might be, that's not quite as tall as this point. So we'd say maybe 800 joules of potential and 200 joules of kinetic. So you could easily calculate the speed at any place on that. Okay, let's look at a couple other common cases. Another common case with that you'll see with this is objects that are falling. If you have objects that are falling off a cliff, we know that that's happening. Up here, it's all potential. The K is equal to 0. Down here, it's going to be all kinetic right before it hits the ground, and then U is equal to 0, like that. So if I get something simple, like let's say this is a, I don't know, 45-meter tall cliff, what I now know is that's equal to Y, and that's equal to H. What I can now say is that U at the top plus K at the top is equal to U at the bottom plus K at the bottom. That's our basic statement to start from an energy point of view. Now we need to locate. This term goes to 0. At the bottom, this term goes to 0. Because right up here, V is equal to 0, and down at the bottom, H is equal to 0. So therefore, those terms disappear. Now, at the top, potential energy is M times G times H. That's going to equal 1/2 mv squared. Now, watch something neat that happens out of that. The m's disappear. And I'm going to get that V squared is equal to 2 times GH. So V would be the square root of 2GH. So that makes the numbers pretty easy to calculate if you want to go through and do that. You would simply have the square root of 2, 10 meters per second squared, times the height of 45 meters is equal to V. 20 times 45 is 900. The square root of 90 is 30, so it's 30 meters per second is equal to V. Now, you could easily do that also from a kinematics point of view, and quite frankly, I don't care which way you do it, but it does make it easy. The equations are pretty easy, so therefore we do it. Now, if we add an angle to it, let's say we do this. And what I now want to know is what happens to the kinetic energy. Well, now I have to go into projectiles just a little bit. Up here, I have U, but I also have some K. So in this case, U is equal to a value, mgh, and K is equal to 1/2 mv squared. Now, in this case, the V is in that direction. It's moving already, so it's not just being dropped from a basic standpoint. When it gets down to this point, my U is going to be 0, but my K is going to equal to what was gained from U, which is mgh, plus the initial kinetic energy it already had, 1/2 mv squared. So it's going to have more kinetic energy at that point. And if you think about it, it makes sense, because when it hits the ground here, if I look at, let's say that's the fraction before it hits the ground, right here is I have a velocity in the x direction. That's the same as what I had up here, because it's going to keep the same x velocity the whole way. But down here, what it's done is it's gained a y velocity, so it's moving faster. When you hit the ground, you would be moving faster if you ran off a cliff than if you just step off a cliff. Now, you're going to hit the ground at the same time, but the difference is there, you're going to have some x component of your speed, so therefore it's going to be greater. Now, one last thing to throw in about this is it's a great way also to incorporate springs. So if I have some type of, let's say we're going to have, I don't know, I'm going to take a dart gun, and I'm going to load something up this way, I'm going to put something on that spring, and I'm going to shoot it up in the air. And what I would do is say at the bottom, I'm going to have spring energy. Now, I'll still call that bottom part of H is equal to 0, so therefore this is going to be max. The potential gravitational energy is going to equal 0, because I called that H is equal to 0. And of course, it's not moving at the bottom, so K is equal to 0. At the top, Well, I'm not attached to the spring anymore, so there's no spring energy. So that's equal to 0. So that's equal to 0. And then I'm going to have gravitational potential energy. U of gravity is going to equal m times g times h. And we also know at the top that kinetic energy stops because the object stops. There's no kinetic energy. So what I can easily now do is set those two equal to each other. So I could say U of the spring is equal to gravitational U. And we'll probably use that for a lab to figure out how high I can launch something up in the air. And again, these formulas are pretty easy. 1/2 kx squared, and that's equal to m times g times h. Now, important thing to understand is the x here is going to be how far did you compress the spring. So don't get that confused with h. And then h is going to be height. In this case, I do need to know m. M doesn't disappear. I also need to know the spring constant. So you have to be given enough to solve that. But again, in review, anytime I start an energy problem, I'm going to say energy at one spot plus kinetic energy at one spot plus spring energy at one spot. Let's say gravitational, and let's say spring. That's going to equal the potential energy at a second spot gravitationally plus kinetic energy at a second spot plus spring energy at a second spot. And generally some of those terms are going to be equal to 0. What you're really saying is the energy before equals the energy after. Now right now we're ignoring friction. Eventually we'll realize that friction creates heat, and heat is essentially lost energy. But in the real world, energy is still conserved. You want to go a step further into atomic physics, then you have to then add this equation, E equals mc squared, which will not be something we'll play around with right now. But I don't want you to leave thinking that this is always true. I can gain energy. That's what the sun does all the time. It gains it from mass. Okay? That's enough.